What is going on, everybody, and welcome to a reinforcement learning tutorial series. In this video, we're going to be starting off with Q learning. Now, every time I do a new series, people are like, what are the prerequisites? Really, for any of the series, there aren't any. Just anytime we hit a concept or topic you don't understand, look it up. In this case, though, there really shouldn't be anything. If you know basic Python, you should be able to follow along with the Q learning tutorials pretty well. Now, when we start getting into deep Q learning, that changes. Now you need to know TensorFlow and Keras and stuff. So just keep that in mind. But at least to start, pretty much anybody should be able to follow along here. So first of all, what actually is Q learning? The idea of Q learning is to have these like Q values for every action you could possibly take given a state, okay? And over time, we want to be able to update those Q values in such a way that running through a chain of actions will produce a good result, okay? Now that's done by rewarding some sort of agent as they get through this environment. And the idea is to kind of reward for the long-term goal rather than in any immediate short-term actions. Now, Q learning specifically is what's called model-free learning. The idea is that the Q learning model that we rewrite, basically the Q learning algorithm, is applicable to like any environment. It's not really environment specific. So the code that we write should be mostly applicable to any other environment that we might want to use it in, as long as that environment's simple enough. So Q learning in the way that what we're about to work with is good for really basic environments, but it's not going to do anything really complicated. For that, you're going to have to start getting into deep Q learning or something like that. So anyways, I think the best way to learn is by doing. So let's jump in. So we're going to need a couple of things right out of the gate. So go ahead and pip install gym. I should already have it. And then also go ahead and pip install, if you can type unlike me, install matplotlib. Grab that as well. We're going to be using that in the series, and I might forget to tell you to get it, but that should be it. So I'm going to go ahead and go into Q learning here and just edit this file. Should be empty for now. Don't need that right now. Cool. So the first thing we're going to do is just kind of poke around, get an idea for this environment. So even though this environment doesn't matter much to our AI, it matters to you to understand how Q learning actually works. So what I'm going to go ahead and do is fix this first of all. There we go. Import gym. And then what we're going to say is the environment is a gym.make, and the environment we're going to use here is mountain car dash v0, and that's title cased mountain car. Anytime you have an environment, the first thing we're going to do is reset, and then we are ready to actually iterate through this environment. So what we're going to say is done equals false, and then while not done, we want to step through this environment. Now, to do a step, we need an action. So for now, I'm going to say action equals 2. Now, again, for your benefit, I think it's useful to understand how the environment works. But in terms of your agent, it doesn't need to actually know. But for your own information, mountain car, this environment has 3 actions that you can take. Now, in a little bit, I'll show you can actually pull all of these gym environments to figure out how many actions are there. But in this case, just for simplicity's sake, I'm just going to tell you there's 3 actions. And action 0 is like push this car left. Action 1 is do nothing. Action 2 is push the car right. So I'm just going to say basically push the car right is our action. And we're just going to do that every time. So we're going to say env.step. We're going to say action. And then env.render. And in fact, I think I'll already populate this. That way we don't have to worry. We'll hit an error if I don't do this. So the next thing we're going to say is new underscore state, comma, reward, comma, done, comma, underscore equals env.step action. So every time we step with an action, we get a new state from the environment. So the state is the things that we're like sensing from the environment, basically. In this case, the state is 2 values, its position and velocity. But again, like I'm going to continue repeating, your model, it doesn't really matter all that much what these values actually are. As long as they're meaningful. Obviously, we don't want meaningless data here, but to the environment or to the agent, it really doesn't matter. But just for your own curiosity's sake, the values that we are getting from here are position and velocity of this car. env.render, so that'll show it. And then if done is done, great. And then if we are done, we're going to do an env.close. I'm going to save that. I'm going to run it from terminal python q learn 1py, and we should get great. So as you can see, this car is trying to get up this mountain or this hill. I'm not sure I'd call that a mountain, but anyway, it just clearly doesn't quite have the horsepower, and instead what it needs to do is build momentum by going up here, swinging down here, and then building up. And the goal is to eventually make it to this yellow flag area. So, okay, so how do we do that? It's actually really, really simple. We just do this. Duh. I mean, obviously. So this is the actual function here for calculating these Q values. But don't worry, you don't actually need to know how to read that or write from it. We're going to convert that to Python in due time. But basically, the way that this is going to work is we want to create this Q table. It's this large table that, given any combination of states, we can just look it up on the table, right? So given any combination of state of position and velocity, for every combination of position and velocity, we just want to look up on this table. Hey, what are the three, in this case, Q values at this position and velocity? And as long as we're trying to exploit the environment, we're just going to pick the one with the maximum, the largest Q value. That said, when we initialize this Q table, we just initialize with random values, which also means those values are random and useless. So actually, initially, our agent is going to do what we call explore a lot, which means do random stuff, and then slowly update those Q values as time goes on. So anyway, that's a lot of information to throw at you. So I think the first thing we're going to do is build the Q table, and then go from there. So first of all, let me just print. We'll print new state. Save that. Did I actually? I think I closed the console. Qlearn. I'm just going to run it again, and we're just printing out now the states. So as you can see here, we've got all these states being printed out. Now, this is the first issue that we're going to come across with Q-learning, and that is that these values, like, that's out to, what is that, 8 decimal places? That's a lot of decimal places. Can you imagine every combination of these two values out to 8 decimal places? That's a lot. So that would make for a huge table that's just going to blow out our memory. And not only is it going to blow out our memory, but the amount of time it's going to take to learn on a table of that size and the amount of episodes we'd have to like run through to do so. I mean, by the time we were done, quantum computing would be like a huge thing already. So so we don't want to wait that long. So now what we need to do is convert these continuous values to what are referred to as discrete values. Basically, we want to bucket this information into buckets of some sort of size. Now, what size those buckets are is going to be yet another one of many variables that we're going to set and likely need to tweak as time goes on. So with that, let's go ahead and get started here. So first of all, so basically at this point, we can start pulling some information from this environment. One of the things that we can do is print env.observation_space.high, and then let's just print the low real quick. High, low. And then one of the other things that we can print is, because I just want to point this out. I think we'll end up using it anyways, but it's it's action_space.n, and that'll tell us how many actions we can actually take. So save. We'll just run that in here. So as you can see, this is the high value for all of the actions, or I'm sorry, all of the observations possible. Now, another thing to note is you might actually have reinforcement learning engaging in some sort of environment where you actually don't know these values. And you actually might just engage in this environment randomly for a while before you even start to learn these values. So in this case, the environment is gracious enough to us to report these values, but we might actually not know. And then here with actions, chances are you'll know your actions in advance no matter what. I can think of a few use cases for like reinforcement learning at least where you wouldn't, but probably not Q learning. But anyway, we can pull the environment of any of these gym environments this way to know exactly how many actions are possible. Okay, so the next thing that we want to do is we want to figure out how we're going to create this Q table. So we want this Q table to be of a size that's at least manageable. So how we're going to make that size, I'm just going to say discrete observation space, or OS size. And in this case, we're going to say 2020. Now, I'm going to change this in just a second. I am kind of on the fence as far as like hard coding this. I think that a real reinforcement learning agent would not have this hard coded because it would change by environment. But you won't necessarily always want these values to be the same number. Like this one, maybe you want 50, and then this one should be 20, and so on. But for now, what I'm going to say is just going to be 20 times the len of any observation space thing. So I'm just going to pick one at random. So this is 2. So it's just 20 times 2. So it's a 20 by 20. Okay. I'm only doing that just because I really want this code to be at least functional on every environment possible. So I just don't want to hard code that because some environments won't only have 2 observation values. They might have 5, 10, 100. Hopefully not, but maybe. So anyway, cool. So all right, so we've got the discrete observation space size. So with that entire range, so from 0.6 to negative 1.2, we want to separate that range into 20 chunks, or 20 buckets, or 20 discrete values, okay? However you want to call it, that's what we want to do. And then we want to do the same thing for the range of 0.07 to negative 0.07. We want 20 chunks and buckets. That way we don't just have this infinitely continuous range that would be forever for us to learn. So now we need to know, how big is that range? How big are those chunks? Like each step through those chunks. So how big is that number? So now we're going to say discrete OS win size is equal to env. Really, are you not going to help me? Observation space dot high. I was really hoping it would just like autocomplete that entire thing for me. Anyway, minus env dot observation space dot low. And then I'll add the spaces around that. I'm pretty sure that would be pep8. Then what we want to say is divided by discrete OS size. That's freaking huge. And then what I'm going to do is I'm just going to print this out just so you can see what I'm talking about. So now print, not in all caps though, print discrete OS win size. We'll run that real quickly. And you can see now, so for positions, each bucket will be of a range that is 0.09 long, and then over here 0.007 long for the velocity chunks. And knowing that, I would say, I'm just going to guess that's probably granular enough. And in fact, I'm not guessing, I already know it's going to work. So so it will be, but sometimes you might find that you have to tweak these values. And again, like I said, sometimes they won't necessarily be the same between two. So I made this change because I want it to work across all environments. And by work, I mean just the code should run. But really, you would take your Q learning scripts and make them far more dynamic. and probably also run like a few, maybe even a few hundred episodes to tweak these numbers a bit. But because this is not our stopping point, I'm not going to spend a bunch of time doing that. Like, we're going to get into deep Q learning and stuff, so I don't want to spend too much time there. We will spend a little bit of time talking about how we can optimize these numbers. But yeah, anyways, moving on. So discrete win size is now known. So finally, we can create the Q table. So again, I'm going to open up Paint because Paint is love and Paint is life. The objective at the end of the day for us is to have this like massive Q table, okay? And so I'm just going to draw just the best table you've probably ever seen in your life. And as you've seen, we have 3 actions, right? You've got action 0, action 1, and action 2, right? And then over here, you've got every possible combination of, well, now it's only 20 by 20, so it's a much smaller set of, it's only 400 things, right? But, this would be, I don't know, combination 1, combination 2, combination 3. And then wherever the agent finds itself, whatever combination of position and velocity that it finds itself in, it's going to come to this table and it's going to see what are the Q values for this specific combination. So for action 2, maybe it's like a 0, it's a 2, and a 1. Okay, and these are the Q values. So then it's going to look, what is the highest Q value? Well, it's a 2. So it's going to perform action number 1 because number 1 has the largest Q value. So over time, at least initially, the agent is going to do a lot of exploration, so it's just going to pick a random value. But then over time, as it picks these things and eventually reaches a reward, then using the Q function for this lovely thing that we'll probably talk about in the next video, it will slowly kind of backpropagate that reward to make for higher Q values for the actions that, when chained together, lead to that lovely reward. But for now, we just need to initialize this Q table, so later we can update this Q table. So the way that we're going to initialize this Q table is we're going to say Q underscore table is equal to np.random.uniform, and then we're going to say low equals, and we're going to start at -2, high equals 0. And again, these are 2 variables that you're going to want to probably tinker with given different environments. And that's why in one of the subsequent tutorials, we will have to talk about, like, how do you analyze these environments? Because it's not, there's no tensor board to pull up and check the loss, So anyway, the intuition behind why these should work is the rewards that we're going to be getting. Basically, when we even printed it out here. Oh no, we only printed out the new state. Since it's part of what I'm trying to yak about right now, let's just I'm going to comment that out, and I'm going to print reward and then new state. So now you can see all of the rewards, and I'll do that in the console. So coming over here, we can see that the reward here is always a -1. And again, to your agent, it doesn't really matter all that much, but to you it might. And so basically, it's good. The reward is going to be a -1 until you reach that flag, at which point your reward will be 0. So that's how. Once it finally reaches that flag, it gets a 0 reward, which is higher than -1, I guess. I think we should get a better reward, personally. But once it reaches that flag, and then we back propagate that chain of events, basically. So anyways, we can see here that the rewards are always -1 until a good thing happens. So we can initialize the table into the negatives because we're pretty confident that that's where, like, the values will eventually lie at about -1, or maybe not -1, but in the negatives for sure. So it just kind of makes sense intuitively to start it there. But again, you'd probably want to tinker with a lot of starting values, to be honest. And then given enough time, it should figure it out anyways. But anyway, coming back to our Q table. So our low is going to be -2, our high is going to be 0, and then finally our size is going to be equal to the discrete OS size, which if we come over here, that's a 20 by 20. So the table is 20 by 20. So when we do make a 20 by 20 table of this discrete observation space size, that contains every combination of observations that we might find. So every combination of position and velocity. Then we need values for every single action that's possible. So the way that we're going to do that is discrete observation space size plus env dot action space dot n. So this should make us a 20 by 20 by 3, so it's a 3-dimensional table, but basically you can just think of it as it's every combination of possible environment observations times 3 actions that we could take. And then inside of those cells, or whatever you want to call them, you're going to have your 3, at this point, random Q values between -2 and 0. But over time, through this agent's exploration and exploitation, those values should get slowly tweaked and optimized based on that. But don't worry, we'll write that in Python, and it makes so much more sense, at least to me in Python, than it does in that stupid formula. But for now, let me go ahead and just print QTable.shape, and let's make sure it's what we expected. NP is not defined. Let's go ahead and import numpy as NP. We'll try one more time. 20 by 20 by 3, and then if you wanted to look at it, you could, but we're not really going to glean anything from it. It's not going to look very meaningful to us. Just understand it's every possible observation combination, and then the Q values for at every possible observation combination and every combination of, or every possible action at every possible combination, we have a random starting Q value. Okay, so I think I'm going to cut it here, and then in the next video we will talk about how to actually start training this model, iterating, and going over these the steps per episode and all the episodes and all that. So with that, a shout out to my longest term channel members. These are people who have been with me for a year or more. That's incredible. I can't believe it's been a year that I've had these, but Stenosco, my longest term member, thank you very much. You're an awesome human being. Misk, NJR, Magali, and Wheatgrass, thank you all so much for your long-term support. You guys are awesome. And you're not just supporting me, you're supporting the free education for people who may not be able to afford it otherwise. So that's really cool. You guys are amazing people. Thank you so much for your support. If you guys want to support the channel, you can click on that blue join button. I know some people don't have access to it for some reason, but if you have it and you want to support the channel, you can click on that right there. Otherwise, if you've got questions, comments, whatever about Q learning, please ask them below. I can't tell you how many Q learning tutorials I ended up having to go through before slowly figuring it out, and I just can't. I hope that my tutorial will be more useful than all the other ones that I found myself on. So, so if you find yourself lost or confused, please ask. Definitely want to help you understand Q learning. I think it's pretty cool. So anyway, in the next video, we will hopefully finish up our agent and actually have it drive it on to that flag every single time. Anyway, I will see you guys in that video.